Hello. Yesterday, Jonathan Birch and myself gave a double act that provided an introduction to sentience. I'd really recommend you see it, especially his section, which was so clear and just totally great. And the question session was great as well. I'm sad we didn't record that. I wanted to take the chance to redo my section a bit more slowly with a little bit more detail, because the first time I give a talk there's always bits I garble. So I want to thank my former student Aileen McClellan and current student Lauren Young for helping me spot the worst offenders. And I'm able to do this today because my day freed up as I have COVID all of a sudden, so I had to cancel a couple of things. So for my section, I set myself the challenge of asking what the evidence is that birds and mammals are sentient. And I'm sure it might seem just obvious to many of you. Your relationships with your pets, for example, don't make sense without sentience. And personally, I am convinced that my cat Sylvie loves me as much as I love her. But there are three sort of counters to this "it's obvious" stance. One is that us humans are pre-programmed to detect intention, emotion, animation, even when it's not really there. So for example, little children will be rapt by a cartoon in which bulls apparently help each other out, rescue each other from a well, and of course the bulls aren't really doing anything of the sort, but little children can't help attending to that kind of scenario. We might see faces everywhere in inanimate trees and in sinks, or we might fall in love with a chatbot. So it could be that when we think our pets are sentient and have emotions, that we're just deluded. My third counter to the "it's obvious" kind of response is that, well, if it's so obvious, why don't we treat birds and mammals better around the world? Because I think societally, it's not that clear that mammalian or avian sentience is really taken seriously in a way that actually matters. So, for example, Canada essentially has no nationwide animal welfare laws that cover a range of species. Dairy cattle get special treatment, but and in the US, animals used in research are protected by the USDA Animal Welfare Act, but not if they're rodents, all 100 million of them, not if they're birds, and not if they're farm animals. And in both of these countries, and indeed beyond, you see very little that protects so-called pest animals from poisons that take days to kill in various unpleasant ways. And if you're interested in this topic, Sandra Baker and Kate Litton are both great researchers to Google. So given this, today I'm going to focus on the birds and mammals that are deemed pests or are intensively farmed or are widely used in biomedical research and testing. And these species fall largely in four orders: rodents and artiodactyls, the even-toed ungulates, and within the birds, the galliforms, the chickens and their relatives, and the columbiforms that comprise the doves, the pigeons. And I'm highlighting the order of these species here because in pulling together my evidence, I'm going to follow Jonathan Birch's sensible, pragmatic rule of thumb that evidence for sentience in one species in a taxonomic order kind of covers or grandfathers in the whole of the rest of the order. And so, for example, for birds, I'm not going to use evidence from corvids or parrots because I'm going to assume that doesn't necessarily extend to the galliforms or the columbiforms, and I'm doing that to be conservative. But I will assume that within an order, evidence from quails, for example, is relevant to chickens and turkeys and vice versa. And I'm going to assume that evidence from common pigeons extends to wood pigeons, which are an agricultural pest, and so on. Likewise, in the mammals, I'm not going to talk about evidence from primates or dogs. I'm not going to assume that would extend to rodents or even-toed ungulates. But evidence from Norway rats, I will assume extends to all rodents, squirrels, deer mice, you name it. And evidence for goats, I would assume applies to pigs and cattle and vice versa. So I hope that's clear. I should also admit that my view of orders turns out is a bit old-fashioned. And actually, the night before my talk, I kind of realised or discovered that modern molecular phylogenies actually include cetaceans, yes, dolphins and whales, within the artiodactyls. So I'm going to just ignore that for now. I really think they're too different, and I don't think that would make for a plausible extrapolation. Okay, so the key question is obviously what would convincing evidence for sentience look like? And I'm going to focus here on conscious emotion because we understand most about the difference between conscious and unconscious emotional processes. We really understand very little about the role of awareness in mood. So, as Jonathan beautifully outlined, good evidence has to not be explainable in other ways, so not be explainable by processes we know are non-conscious, and it shouldn't be explainable by clever looking or emotional looking but pre-programmed innate responses. Furthermore, I don't know if you can hear my cat yowling, he is too sentient, that cat. Furthermore, evidence should map onto the apparent properties or the likely functions of human consciousness, especially conscious emotion. And this, as Jonathan outlined, is broadly to do with integrating stimuli, forming sort of constructs about the world, and also supporting behavioural and cognitive flexibility. So what do conscious emotions specifically allow us to do? So Nico Frieda argued beautifully in 1994 that conscious emotion seems to allow us to respond flexibly in order to increase our exposure to positive states and reduce our exposure to negative ones. And so here an explicit representation of valenced outcomes allows us essentially to do whatever it takes to feel good, to cast around and find different options that work, and also likewise to do whatever it takes to avoid feeling bad. And what feels good or bad is assumed to be respectively good or bad for fitness. So these are proximate fitness enhancing strategies. 20 years later, Edmund Rolls essentially agreed and said, yes, conscious emotions allow subjects to generate multiple alternative ways to, for example, find a reward. But he argued that they do this in specific ways, that they allow us to recall and to reflect on and to reorganize information about the self and about the world in order to make new inferences and to devise new strategies for getting rewards or avoiding punishes. So, for example, he would argue that conscious emotion is essential for helping us manipulate information in our mind, figuring out, well, if A did B and then got zapped, I need to not do B, but I might try doing C, for example, and to do all of this without trial and error learning. So Rolls sets the evidence bar pretty high because he wants our indicators to not just be explicable by associative learning. So let me give you a sort of everyday example of what these neuroscientists might be talking about. So if you imagine that you have an intense abdominal pain all of a sudden, you might automatically show a pain face and change your posture and how you move and maybe where you hold yourself on your body. And these are pretty stereotyped. They occur across cultures, across people. They're not learned, and we wouldn't use these as indicators of the felt experience of pain. But the felt experience of pain allows us to do other things as well. So, for example, we can modulate these pain responses that I've just talked about. They're not automatic, they're not unsuppressible. So for example, we might exaggerate them if we want to get sympathy, if we're an Italian soccer player, for example, or we might mask them if we want to protect our loved ones who, for example, are terrified that we've got a return of tumours. We can also interocept, so we can kind of examine our own pain, and with this examination we can do things like report on it, we can describe it in words, in writing, or we can point at frowny faces in one of those pain severity charts. We can also use our interoception to flexibly take appropriate action. So for example, if you feel a searing pain in your abdomen and you're 9 months pregnant, one strategy is to grab your go bag and get to the hospital, implement your birth plan. If you're a man, it might be way more frightening and mysterious, or it could be that oh, I've just got wind. You should be able to identify it from its quality, from what you're expecting, from your context and from your past experience. And past experience is important because we can recall past pains, compare them with current pains, and use that to decide, for example, how worried to be. Is this post-operative pain is pretty bad, but it's better than yesterday? Or is it a new pain that's getting worse, in which case I might react quite differently? So that's a sort of informal picture. How do we turn that into empirical evidence that we can get from animals? And this is sometimes a bit trickier. So the evidence for this that I will be reviewing will cover 3 types of phenomena. One is animals showing arbitrary operants to gain rewards or avoid punishes. Another is additional evidence of goal-directedness that doesn't necessarily involve association, or ideally doesn't. So for example, de novo planning, and also evidence of interoception in animals. And together these represent cases where animals are showing evolutionarily novel, developed by an individual behavioural responses that either indicate interoception or are consistent with having felt goals. Now, in compiling this evidence, I need to apologise in advance that some of the work is actually kind of nasty. It's from the 50s, 60s, 70s. Welfare was not a consideration in many of these studies. Nevertheless, I'm hoping to harness them for something good. So let me dig into these 3 in a little bit more detail. So, obtaining rewards or avoiding punishes by learning an arbitrary, by which I mean evolutionarily novel operant. Why should this be evidence? Well, one reason is that as far as we know, this doesn't occur without conscious awareness of the reward or the punisher. Now, absence of evidence is not evidence of absence, and it could just be we need more human work, and there's definitely a lack here, but certainly one reason to consider it as a candidate. Furthermore, operant learning exemplifies flexibility, and it does lead to evolutionarily new individual-specific responses. And so this is most persuasive when the learned operant response we see is unlike anything we've seen in nature, so it can't have been pre-programmed by evolution, and or the reward is not like anything seen in nature. So for example, it's electrical brain stimulation or analgesic drugs. My middle category was evidence that animals are using non-associative strategies to gain rewards or avoid punishes. And it is a bit tricky to operationalize this, but some good candidates are gold evaluation studies, and I'll explain these when I get to rodents. Another might be using information about the lay of the land in novel ways to facilitate, say, the getting of food. So for example, if an animal's learnt a familiar maze, but then is given a brand new shortcut, does the animal immediately recognise that shortcut as a great way to get food faster? Another example might be animals using information gleaned by remotely viewing ways to get food, so that when they're given that opportunity, they are more skilled at it, even though they've had no prior opportunity for trial and error learning. So this might include watching conspecifics get food or other types of problem as well. And it might include evidence of planning as well. And I'm going to admit, I just didn't have time to dig into this, but I'm also kind of 80% sure that there aren't good data on this for most of the species in these orders. And my final type of data is to look at evidence for interoception. And for here, I'm going to cover using internal states as discriminative stimuli. So this is a bit jargony if you don't have a learning background. So let me tell you what I mean. And actually, it's nothing more complicated than what we talked about in the human pain example just now. If you experience a pain, you inspect that pain, and then you decide which of a number of different learned responses to put into action. Should you take a drug? And if you should that drug be an opiate, an antacid, a gas-relieving pill? What should it be? Or should you just grab your hospital bag, carefully bought from Etsy, and head off to the hospital to give birth? Or should you call 911 because something very frightening is happening? So how can we get at this kind of phenomenon in animals? We can do this through a sort of advanced type of operant learning in which animals learn that particular operants only work when other stimuli are present in the world, and these are called discriminative stimuli. And animals can learn that particular operants should only be performed in the presence of particular internal discriminative stimuli. So for example, in this case, this unspecified rodent here is having to learn that half the time one of those levers delivers food, the other half of the time the other lever gives food, and this isn't random. Which lever will deliver food is predicted by cues coming from within the animal's own body or brain. So what might these cues be? These are cues that have been manipulated by the experimenter. And so in tasks like this, an experimenter will train a hungry animal that when they're put in a test chamber in which one of two levers yield food, or perhaps one of two runways, varies depending on their own state. And in tasks like this, animals have been shown to successfully learn to choose the operant based on, for example, whether part of their intestine is being pulsated by a small inflatable balloon in one unusual and slightly disturbing primate study from the 60s, or whether they've been given saline or, by the same route of administration, a psychoactive drug with subjective effects. And there are thousands of studies here from 11 different species, including humans. And the reason to take such data seriously is, aside from their plausibility, human data on similar tasks involving psychoactive drugs show us that people can typically only discriminate types of drugs that are psychoactive. That is, they have subjective felt effects. And within these drugs, people can typically only discriminate doses high enough to induce subjective felt effects. Now I say typically because there are some counterexamples where people seem to get the right response even though they report not feeling anything at all. And this means at least the human data might sometimes be evidence instead of conscious feelings. Instead, it could represent some kind of blind sight like successful guessing. So in animal studies, I'll be using this and then hoping to go beyond it to argue that we have true interoception. Okay, so let's look at what we know about the rodentia, and I'm going to focus on rats because they have been so deeply researched by so many hundreds of researchers. So rats are kind of the poster children for operant responding, and of course we know that rats can very readily learn things like pressing a lever in order to get food, in order to escape from electric shock, but they can also do it to obtain recreational drugs, and this has been confirmed as goal-directed. I'll show you how in the next slide. Rats can also get a shortcut to learning novel operants by watching others do this, as though they don't have to do all of this learning by trial and error. And again, I'll give you examples in a couple of slides. And rats will lever press for evolutionarily novel rewards. So I mentioned drugs, they'll also work for electrical brain stimulation as well. Furthermore, when they self-administer some drugs, particularly analgesics, they seem to do this in a state-dependent way that's very consistent with them having a true feeling of pain. So there are many examples of this, but I think a particularly amazing one comes from Francis Colpert. And this work showed that if you compare control rats with rats that are experimentally given arthritis, so their feet swell up, as you can see in the bottom picture, rats with induced arthritis, given the chance to self-administer opiates, will do so at a much higher rate than control rats. But they will reduce this self-medication if they are pre-infused with the same drug, so they're already analgesed, or if they're pre-dosed with an anti-inflammatory drug that successfully tackles the swelling in their feet. So pretty powerful stuff. And this would make it seem as though the analgesia self-delivery is pretty directed at the goal of reducing pain, but is it sort of soppy to attribute goal direction to operant responding? So evidence that drug self-administration and also operant responding for food is actually goal-directed has been attained in the 80s and 90s in some really elegant experiments, if not always very nice for the rats. So let me give you an example. In this particular case, rats have been trained that if they do one operant, for example, lever pressing, they will get sucrose, and if they do another operant, let's say chain pulling, they will get pellets. And rats will learn both of these operants just fine, and they will shuttle between getting food and getting sugar in the operant apparatus. Now, let's suppose that outside of the apparatus, they are then given one of these foods in association with poison. So the food effectively makes them sick. And rats, like us, are very good at learning, that was bad food, it made me sick. So if rats have a sense of the goal of what food they want when they go into an operant chamber, rats that have been made sick by sucrose should only do the operant that gets them pellets, and rats that have been made sick by pellets should only do the operant that gets them sucrose. And they should do this immediately from the very first response. It shouldn't be the case that they go in the chamber, do a little bit of both, discover that, I just can't face pellets right now, there's something about them, and gradually wane or show an extinction. It should be there de novo the moment they go into the chamber, and that's exactly what we find. So here we see data for helping themselves to sugar and pellets before they've been poisoned. And here is how they respond after they've been poisoned. And the thing to notice is that this happens absolutely immediately in the very first minute of entering the chamber. So that's pretty great, amazing success evidence of goal direction. It's called the goal devaluation procedure. What else can we use to infer that rodents will flexibly work out ways to get a reward? So one type of evidence is that rats can figure out new ways to get food by watching other rats do an operant. So for example, in this setup, animals have to learn to push one lever when they hear a long tone and the other lever if they hear a short tone from the loudspeaker. So here the tone, once again, is a discriminative stimulus. Rats will learn this just fine, and rats that are good at this task are then exposed to some observer rats who are put in the chamber next door, and they can do nothing but watch these rats do this complicated learned task to get food. So then the question is, when the observer rats are put in this chamber, will they then immediately know, okay, when I hear the long tone, I should press that lever, and when I hear the short tone, I should press the other. So different studies find different results. All of them find that the observer rats benefit. So they've definitely gained information about reward getting that they're using in a flexible way. Sometimes it just accelerates how quickly they get the hang of the novel task. In some work by Sagerson and Rob Honey from Cardiff, one group of observer rats actually did better than chance even in trial 1. So they figured out the task simply by watching. So pretty amazing. Turning to another use of discriminative stimuli, this time back to using internal states as discriminative stimuli. Rats are very, very good at doing this. So for example, a hungry rat in a test chamber can learn which of 2 levers will yield food to eat, and that delivery depends on whether they've been given saline or a psychoactive drug. Hundreds of studies here, as I mentioned before. They can learn to press the right lever according to what their own last behavioural action was, which I think is amazing. They can also learn to press different levers for food according to when they were last fed, so whether they're very food deprived or whether they're just mildly peckish. They can learn to do different actions according to whether they're hungry or thirsty, and they can even learn to do different responses according to whether or not they're in drug withdrawal, with different states predicting which of 2 operants to use. So does this indicate true interoception, or are the rats just doing this in a blind sight, like successful guessing way? They can't feel a thing, they're just guessing, and yet their guesses are spookily right. So it does seem that they're using true interoception here, and the evidence is twofold. One is that they show state-dependent changes in their ability to use drugs as discriminative stimuli, and I'll give you an example in a bit. And the other is that they generalize from the drugs to which they've been trained to use as a discriminative stimulus to other experiences, such as other drugs, that arguably have very similar subjective effects. And I'll give you examples of those too. So first, the first one. Rats showing state-dependent changes in their abilities to use certain drugs as discriminative stimuli. So this is quite a mouthful, but all I mean here is this phenomenon. Supposing somebody gave you a pill and asked you to tell them whether or not it was an Advil. If you had no aches or pains anywhere, you'd find that very hard. Is it Advil? Is it a placebo? How would you tell? But if you had a headache, say, you could take the pill, and if your headache reduces in about 15 minutes, there's your answer. So your ability to discriminate Advil from a placebo is state dependent. You can do it much more easily if you're in pain, and exactly the same is true of rats. So in this study, rats were trained to use aspirin as a discriminative stimuli, and so trained that when they're infused with saline, one operant will give them food. If they're infused with aspirin, the other operant will give them food, the other lever. Normal rats find this quite difficult. Not impossible, they will pick the aspirin lever when they've been given aspirin correctly in 60% of trials. But rats who've been given arthritis by an injection to the foot again find this easier. They have a 70% success rate at discriminating aspirin, and that's statistically significant. Conversely, in another study, rats were shown to be able to use a state of pain as a discriminative stimulus. So when I'm in pain, one lever will get me food. If I'm not in pain, another will. But they struggle if they've been pre-dosed with an analgesic. So this is the same phenomenon, but kind of reversed. So extraordinarily consistent with true interoception. Furthermore, rats that have been trained on one type of drug will generalize to experiences that we're almost certain have the same subjective effects as the training drug. So, for example, if rats have been trained to use one particular stimulant as a discriminative stimulus, let's say caffeine, if they're then given another type of stimulant, even though it has completely different pharmacology, they will then pick the caffeine lever for food, not the saline lever. And they're not just reporting, oh, I feel generally weird, because if they're given non-stimulant psychoactive drugs, they will push the saline lever. So it's very specific. And animals don't just generalize between drugs as well, they generalize between drugs and other experiences as well. So for example, I mentioned that rats could use a state of being hungover as a discriminative stimulus. So rats that have been trained in the fewer hours or days after a large dose of alcohol, this lever will give you food, but when you're feeling fine, the other one will work. If these animals are then put through morphine withdrawal and asked which lever to pick, they won't pick the saline one, they will pick the hangover one. Very consistent with both opiate withdrawal and alcohol hangovers being very, very unpleasant. Rats also pick, oh, my video is in the way there, sorry. So rats can also be trained to discriminate an anxiety-inducing drug called PTZ, which is short for pentylene tetrazole. And they can discriminate that from saline, and it seems to induce signs of anxiety in them, just as it induces terrible feelings of anxiety in us. Rats who've been trained to discriminate between PTZ and saline will then pick the PTZ lever for food, not the saline one, if they've been exposed to electric shocks, or if they've been exposed to a cat, or if they've been exposed to a strange conspecific who beats them up. So collectively, all of this represents very, very, very strong evidence that rats and therefore rodents are sentient. I think this evidence is simply as good as it can possibly be without speech. And ironically, we have this corpus of evidence because, and I think it may be better than what we have for primates, because for decades people have been so comfortable subjecting these species to all kinds of unpleasant things in the lab. So I think they're vanishingly unlikely to be non-sentient. All right, let's turn to the even-toed ungulates. And the data here come from mostly goats and pigs with one or two cow examples. So can artiodactyls learn to perform arbitrary operants? Absolutely. So here in this lovely study from Denmark, this cow has been trained to do an arbitrary operant to lie down. How this works is she is prevented from being able to lie down by a sort of girdle around her midriff that's attached by a rope. And if she presses a paddle with her nose, that you can't see in this dark area, but that's where it is at the front, if she presses a paddle with her nose, the rope will relax and she will be able to then lie down. So cows can learn how to do this. Goats can push panels for oats, pigs can push panels to release other pigs, and pigs can also do operants for recreational psychoactive drug administration and also for electrical brain stimulation. What about using other types of flexible strategies to get rewards? So for example, can they learn by observation and so figure out shortcuts, flexible shortcuts to getting rewards without tedious trial and error learning? Pigs can absolutely do this, and so too can goats. So let me give you a lovely pig example from a very recent paper from Germany. So here, pigs had to figure out a puzzle box in which a plug has to be removed vertically and then a slidey thing has to be slid out horizontally in order to reveal a chamber in which there are treats. Now pigs learn in advance that there are treats hidden in the box and that they're pre-exposed to the box all open. But how can they figure out how to open the box? In this study, a number of different strategies were explored to see what types of things pigs could witness and get a head start on figuring out how to open the box. So some of these were typical social learning. If they watched another pig opening the box, would that help them? But I think my favourite piece of this work was a ghost demonstrator in which a clever series of invisible strings and pulleys opened the box as if by magic. So the observer pigs just watched the box being opened and the food being revealed. So in this experiment, all the observer pigs, compared with naive pigs who didn't get this chance to look at the mechanisms of the box, all of them were more successful in solving the task compared to naive non-observers. So this shows that pigs can use information about the world flexibly to get to a food reward even without trial and error learning. There's also some lovely evidence consistent with goats pulling up alternative strategies when they need them to get food. So let's see what you think about this. So in this study, goats were trained that a lovely treat, dried pasta, was underneath a plastic box. And in the training trials, goats very rapidly learned to do things like move the box or kick over the box to get to the crunchy treat inside. And in these training trials, a researcher was always sitting there watching them, and the human was always just observed because the goats were just busy getting the pasta. Then in the test trials, the goats were faced with an unsolvable version of this problem in which the box was glued down so they couldn't actually get to the pasta. What would the goats do? So these are goats that have learned that humans give them food and that humans can kind of be useful. So what the researchers found is that in the unsolvable problem condition, goats started alternating their gaze between the box and the human as if to say, hey, aren't you going to help? There's pasta here. I can't get at it. I don't have opposable thumbs. And one goat even went so far as to kind of demand a bit more active intervention. Now, maybe I'm reading things into this behaviour that aren't really there, but this seems to me very consistent with goats being able to pull up alternative strategies when a learnt behaviour they've acquired doesn't work and they want to find other ways of reaching a reward. What about interoception? So pigs can be trained to use internal states as a discriminative stimulus. The only work to explore this has used this drug PTZ as the training compound. So this is pentylene tetrazole, which in us induces feelings of anxiety, which given to pigs seem to also induce stress responses as well. So pigs could successfully learn to do different operant responses according to whether they'd been dosed with saline or PTZ. Okay, so that's one nice bit of evidence, but could they be doing this again by blind sight, like guessing? So stronger evidence, more consistent with true interoception, is that in a study of 4 trained pigs who were then exposed to electric shock, after the shock, all 4 pigs picked the PTZ response for food, not the saline, which is very consistent with the rat data and very consistent with a feeling of anxiety leading to a selection of the correct operant. Furthermore, in another study, which is kind of intriguing but also frustrating because the sample sizes are terrible and the stats are pretty much incomprehensible, but nevertheless, bear with me. In another study, 1 out of 4 trained pigs was shown to pick the PTZ lever after hearing dog barking. 1 out of 3 did so after being driven round and round in a truck, and 2 out of 4 also picked the PTZ lever after exposure to a strange pig. So collectively, given their flexible strategies to get rewards and their ability to introspect the effects of an anxiogenic drug and generalize that to shock, this is very strong evidence of sentience in artiodactyls. Okay, so moving on to the birds, I'm going to start with columbiforms and I'm going to pull together some data from the common pigeon that's been widely used as a research subject in the laboratory. Pigeons can be readily trained to perform arbitrary operants. For example, they can be trained to peck a disc or press treadles with their feet or to raise their heads in a particular way to avoid punishers in the form of electric shock. They will also pick for electrical brain stimulation, and some of this stimulation would induce cooing and bowing as though it was stimulating maybe sexual or courtship feelings. Pigeons will also do an operant to self-administer cocaine as well. So, do they show evidence of goal-directedness? So, outside of the laboratory, another stream of research has focused on the amazing abilities of pigeons to get home from very long distances, hundreds, sometimes thousands of kilometres away from their home. Now, this work started in the 60s, and pretty much all of it has focused on their cognitive abilities and what sensory cues they're using to navigate. But what this work has shown is that pigeons are remarkably good at using multiple different cues to navigate home, and they can be quite flexible in which they can use. So for example, if you knock out their sense of smell, they'll use other strategies. If they're displaced way off a path they're expecting, they'll somehow find their way back to the path home. I mean, it's pretty extraordinary. So I wonder, even though no one's ever explored this, whether this behaviour meets Rawls's criteria for conscious emotions, in that it's sort of consistent with pigeons having a conscious representation of how good it is to be at home and how very much they want to be there. Now, I'm sure someone will tear that to pieces, so I will leave that idea for future researchers and move. Okay, so what about more empirical evidence of goal-directedness, or at least the ability to flexibly use information to get a head start on acquiring food? So just as in rats, pigeons are able to get a head start on a complex operant task by watching other pigeons solve the problem. So here again, the pigeons who were the demonstrators were trained to perform one type of operants in the presence of one cue, a light or a tone, another type of operant in the face of another cue, a light or a tone. And once these pigeons had got the hang of it, they were presented to observer pigeons who could watch the trained pigeons do their thing and successfully get food. So could the observers then, plunked into the apparatus, successfully do the conditional discrimination that involves the use of a discriminative stimulus? Well, a bit like some of the rats, they couldn't instantly perform above chance, but they did show an amazing ability to learn super fast compared with pigeons that had never seen anything like it. So again, this shows that pigeons can use information that they're acquiring from the world in flexible ways to enhance their ability to get food, even without trial and error learning. Finally, pigeons can learn to do drug discriminations in which various psychoactive drugs are discriminated from saline, and these include THC, amphetamine, a host of opioids, and many other drugs, sometimes up to 4 different types at once. So pigeons are amazing at doing these tasks, and pigeons can be trained to discriminate between 4 completely different psychoactive compounds, and when they're exposed to each of them, they have to push a different key in order to get food, and pigeons can learn this just fine, so they're fantastic. Furthermore, they can, like rats, even use their own recent behaviour as a discriminative stimulus. So pigeons can be trained that if they've recently pecked on a disc, they should do one thing to get food, and if they haven't recently pecked on a disc, they should do another response to get food. So they're basically recalling, did I recently peck or not, in order to decide what to do next, which quite frankly, I'm not always sure I have this ability. I sometimes find myself in the kitchen, I'm like, how did I get here? As further evidence that this is true introspection, just like rats and people, pigeons will generalize between diverse drugs that feel similar to us and not between drugs that feel different. And they will also show state-dependent changes in discrimination. Now, the evidence for this I showed you in rats revolved around pain and analgesia. The evidence for this in pigeons revolves around anxiety and anxiolytic drugs, specifically benzodiazepines. So in humans, a pre-existing emotional state of fear or anxiety enhances the subjective effects of benzodiazepines. In other words, you can detect them more readily if you already had an anxious state that the edge could be taken off, as it were. So this is just like the way we identify aspirin more readily from saline if we're in pain. And pigeons seem to show something remarkably consistent. So pigeons can discriminate the anxiolytic drug benzodiazepine from saline, but they do so more easily if they've been recently electrically shocked or recently exposed to a loud noise. So this is incredibly consistent with them using a subjective state or fear or anxiety and a background fear state, making the anxiolytic drug easier to detect. So I've got to say that for pigeons and their relatives, I think there's actually stronger evidence for sentience than we see in the artiodactyls because they've been so well studied. That last benzodiazepine study, I have to say, I actually found upsetting because it put into context all the other horrible research I've been reading in which pigeons have been involved. So I'm going to argue that columbiforms are indeed sentient. Okay, finally, sorry, disgustingly sniffing because I am quite COVID-y. So finally, turning to the galliforms. Data here come from a few studies of chickens and a few studies of quail. Now, we have known since the work of the Brellans, who were former students of Skinner, that pigeons can be trained to perform a variety of innovative and potentially entertaining operants. So that was a pigeon pulling a string to get food and also to deliver a postcard to that small boy from the 1950s. In other work, pigeons were trained to do a kind of tug of war. And in one, a hen was trained to look frantically in loads of directions to get food. And they called this, it was an exhibit, they called this the atom bomb neurosis. This was the 1950s, remember? Okay, we also know that chicks will learn to peck to turn on a heater. And that chicks will also peck for electrical brain stimulation. And this also induces calls associated with the mother and with food, consistent with that stimulation, working on sites associated with pleasure. As for adult hens, there's further evidence that their food-getting behaviour is actually goal-directed, using reward devaluation tasks that have been like those used for rats. And so this shows when they're seeking out food using a learned response, they really do have the goal of getting food in their mind. It's not just a food-getting habit. Furthermore, in operant tasks where food is the reinforcer, hens will show impulse control, which shows they can flexibly override their automatic responses to get food, and they can also use food-getting calls from other hens in a functionally referent way, so getting excited about them if they haven't seen food, but ignoring them if they've already seen the food that is being referred to by conspecifics. So these are the Finally, a couple of studies in quail have shown that these birds too are capable of getting a head start learning a complex operant simply by watching another bird do it. So they can figure out the steps involved in getting a reward by watching a demonstrator. Again, they're not instantly good at it when they're put in the apparatus themselves, but they're certainly quicker at figuring out the task involved. It's again one of these tasks involving two operants, which one is correct being determined by an external discriminative stimulus. So again, consistent with flexibly learning about the world and putting that to novel use when you have a chance. As for the use of internal discriminative stimuli to modify an operant, there's only been one attempt here and it was a fail. So there was a fail in quail. I'm not sure that reveals much, but it's sad that we don't have anything stronger. And that's it for the galliforms, actually. That's really it, unless I slightly modify my criteria and I include a Pavlovian task. And I'm going to include this because it shows evidence of state dependency. So in some lovely work from Christine Nichols' lab, hens that either did or did not have keel fractures, healed keel fractures, but still damage to the bone, were trained that in a T-maze, one arm would be associated with being given opiates and the other arm was a control. Given the choice between those two arms in extinction, which arm would they choose? The healthy, unfractured hens were indifferent. In 7 trials, they picked each arm on average 3.5 times, so perfectly at chance. In contrast, the hens with the healed fractures chose the opiate arm maybe 4.5 times out of 7 on average. So not a massively strong result, a little bit disappointing. It's honestly all we have for chickens. So I've got to say, of all the 4 orders I've covered, I'm most doubtful about the galliforms. I don't think the lack of evidence indicates they're not sentient. I think the lack of evidence shows they have not been studied with that question in mind. There is very strong evidence that they can flexibly seek reward, so I'm going to say they have positive affective states, but we're missing a ton of evidence about negative affective states, which is good in a way because it means people haven't been exposing chickens to pain for the sake of research, but it's also frustrating. And so using the high evidentiary bar that I've set, aiming to convince a real skeptic, I'm wondering if future work could exploit the difference in likely pain between hens with fractures and hens without to do some work on operant self-administration of analgesia, perhaps using pre-infusion or anti-inflammatory drugs like Colpert did, or whether we could even use the presence or absence of analgesia as a discriminative stimulus. If we could in those birds, I think that would be really, really powerful stuff. Okay, so to wrap up, what's the evidence that the mammals and birds of the orders I looked at are sentient? We can see powerful evidence that rodents are sentient, and this means that the 100 million plus that are used in research, they really need better protection. The hundreds of millions, perhaps billions, who are killed inhumanely through pest control really need better protection as well. The same is true of artiodactyls, very strong evidence of sentience, and so Ontario Federation for Agriculture, it is not anthropomorphic to argue that these animals are sentient. Turning to the columbiforms, pigeons, doves and their relatives, again, remarkably strong evidence for sentience in these animals. And so birds should be covered by the USDA Animal Welfare Act, I would argue from this. Finally, chickens, a little bit disappointing, and it's the classic that we need more research. So pulling together the evidence for this talk, I found incredibly thought-provoking because it really raised a bunch of questions in my mind. Was it right to assume that one species covers a whole order? What do we do if that order is weirdly heterogeneous, like the artiodactyls, and admitting cetaceans are probably in there? What kind of standard of evidence do we really need? And why is it people that differ in that? It strikes me that some of it is difference in our educational training. Some of it is probably differences in our pre-existing sympathy to animals. Some of it might be what we feel we have to lose professionally by going beyond the data that we can support 100%. And some of it is driven by conflicts of interest as well. So it's a fascinating issue. And of course, it might also depend what action we want to take as a consequence. So to when do we invoke the precautionary principle and protect animals we're not sure about, or when do we use equivocable, is that the word? I'm really losing it, I'm quite ill. When do we use partial evidence to maybe make decisions on a personal front but not require them at a policy level is completely fascinating. Jonathan covered this beautifully in his part of this talk, and you're going to see these issues recurring in all the other 4 talks that are coming up in the rest of our series. So thanks for bearing with me. Oops, some unwanted animations there. And I would just like to add my Sincere thanks to Christian Nowroth, to Heather Browning, to Liz Paul, to Pat Turner, to Tim Guilford, and to members of the Animal Cognition group of the GTA, who, even though they didn't field questions, are always in my mind as a kind of critical audience. And of course, many, many thanks to Jonathan Birch as well. Those of you listening, I really hope you enjoy the rest of the talks. Thank you very much.